So we've talked about higher order derivatives, second derivatives, third derivatives, fourth derivatives, etc., as just being the derivative of whatever derivative came before it. So the second derivative is the derivative of the first derivative. The third derivative is the derivative of the second derivative, etc. What we want to do here is calculate second derivatives for implicit functions, which is a little bit weird because there's some nuance to it. So we'll jump into it and try doing it. So first, to calculate the first derivative, this is what you've already done before. So 2x minus 2y y prime equals 0. And so then we solve for y prime. We get that y prime equals x over y, just like we've been used to before. So algebraically solve, rearrange, and that's what you get. Now, if we want to find the second derivative, though, we need to take the derivative of both sides. So d by dx of y prime equals d by dx of x over y. So on the left side, we just get the second derivative, or y double prime. On the right side, we need to use our quotient rule. So that's y times x prime, which is just 1. Let me write that in. So y times 1 minus then the derivative of the y, so y prime, times x, all divided by y squared. Now the problem here is this isn't a function because it's got this y prime in it. But we already found y prime earlier, so I can come down here and just plug it in. So in other words, the second derivative of y, of this function y, or of the implied function y, is y minus x squared over y, all divided by y squared. And we can clean that up a little bit if you really wanted to, but looking at it again, it's not going to get that much cleaner. But that's the idea behind calculating the second derivative of an implicit function, or the third derivative, or the fourth derivative. It's just always going back to this value that we defined earlier. So I'm going to do another example real quick here. D by dx of this function of y is equal to d by dx of x e to the 5y. I'm just using different notation this time. Same idea, but slightly different notation. So dy by dx is equal to, now we need to use the product rule. So the derivative of the first term, that x, that first function, is going to be 1. So we're going to e to the 5y plus the derivative of the second term, which is e to the 5y times x. So x times d by dx of e to the 5y, which is going to equal e to the 5y plus x times e to the 5y times 5y, because of the chain rule, 5y prime. So that should actually be dy by dx to keep my notation consistent. 5 dy by dx. So again, I took the derivative of e to the 5y, which the derivative of e to some function is e to that same function times the derivative of the function. Okay, so this is our first derivative, which means we need to do a little bit of cleaning up, though, to solve this, because we've got dy by dx on both sides. So I have dy by dx minus, not plus, minus x e to the 5y dy by dx equals e to the 5y. Factoring out the dy by dx, we get dy by dx is equal to e to the 5y divided by 1 minus x e to the 5y. So this is actually what we want to have for our first derivative here. So now we need to work on our second derivative. So that's going to involve taking the derivative of both sides. So d by dx of dy by dx is equal to d by dx of e to the 5y divided by 1 minus x e to the 5y. The left side is just d squared y over dx squared, or in other words, the second derivative of y with respect to x. And the right side, we have to use the quotient rule again, unfortunately, so it's going to be 1 minus x e to the 5y, the term on bottom, times the derivative of the thing on top, which is going to be e to the 5y times 5 dy by dx, minus, flipping that around, which this is going to be a mess. So how do I want to write this out? Let's try to fit it in. If it doesn't work, well, we'll figure it out then. So e to the 5y times the derivative of this bottom term, which we actually already found at 0 minus this term right here. So e to the 5y times e to the 5y plus x dx. Okay, yeah, we need to completely rewrite that. So this is a good lesson of when you get stuck in a corner, take a step back and start over. So d squared dx squared, d squared y dx squared. And then we're going to get the term on the bottom, 1 minus x e to the 5y, times the derivative of the term on top, which is e to the 5y, times 5 dy by dx, minus e to the 5y times 0 minus, and then we have to use the product rule again, so x e to the 5y, 5 dy dx, to make that a minus, plus, flipping those around, e to the 5y. So what I was saying earlier is we already solved x, the derivative of ex to the 5y. It was right here. And so we should see that replicated here. E to the 5y plus x e to the 5y, 5 dy dx. Great. And then divide that whole term by 1 minus x e to the 5y squared. So now all we have to do is plug back in our derivative from earlier. Is this going to clean up? Not really. It's still going to be a mess, but that's part of what we deal with in calculus. So 1 minus x e to the 5y times e to the 5y times 5 e to the 5y over 1 minus x e to the 5y minus e to the 5y times x e to the 5y times e to the 5y over 1 minus x e to the 5y plus e to the 5y. All over 1 minus x e to the 5y squared. Not pretty, not super fun. There's probably a way to clean this up a bit, but I wanted to illustrate the key point of the general principle, which is take the derivative, solve for the first derivative, take the derivative again, and then plug in whatever you get for this into the expression up there. This is probably a bit more complicated than you would have to deal with on the AP test, but it's a good illustration of just churning through and just working through the problem.